we're going to move our discussion into thermodynamics. So the next few chapters will deal with thermodynamics. And to start, we'll define temperature. Now, your book doesn't really give a strong definition of what temperature is because we won't have the tools to define temperature until a few chapters from now. Temperature is technically the measure of the average kinetic energy of the particles in an object, but we're going to hold off on that technical definition for a bit. Just know that temperature is one of the base 7 SI units, like length, time, quantity, and so on. The SI unit for temperature is called the Kelvin. It's represented by a capital K. Now, Kelvin is defined as 0 at absolute 0. Now, theoretically, absolute 0 is classically when the vibration or movement of molecules in an object stops. Now, we learned quantum mechanically that never happens, but classically, it's the limit where motion would stop in an object. That is called absolute 0. It's the lowest temperature you can go. And 273.16 Kelvin at the triple point of water. And we'll define what the triple point of water is a little bit later in this video. So that's the definition of the Kelvin. Now, you might be more familiar with two other types of temperature measurement. If you've had a chemistry course, or you most likely know if watching the Olympics abroad, they might give temperatures in Celsius, also known as centigrade, although that's largely not used as a definition anymore. Celsius is defined with 100 degrees Celsius as the freezing point of water. 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius as the boiling point. Now, interestingly, when Celsius first came up with this conversion, or this scale, he flipped those numbers. 100 degrees Celsius was the freezing point, and 0 degrees Celsius was the boiling point, so things went backwards. That didn't catch on, but his idea of making 100 steps, if you will, 100 degrees between the freezing and boiling points of water was popular, and that stuck. Now, note that this occurs at sea level. Standard temperature and pressure, it's called STP. The boiling point is actually lower if you're above sea level. So, for example, if you live in Denver, Colorado, the Mile High City, named that way for its vertical height above sea level, not because marijuana is legal. Mile High City, the boiling point of water is a little bit lower. It's about 97, 96 Celsius or so, which means that since the temperature of the water is lower when it boils, you need to cook your food longer in that boiling water to make sure it's cooked. So if you've ever seen directions on, noodles, for instance, or some other thing that you have to boil, sometimes it'll give specific examples, at high altitudes, increase these times. But in the US, Fahrenheit is the temperature scale we're most familiar with. Now, the Fahrenheit temperature scale is defined to have 180 degrees between the freezing and boiling points of water, with 0 degrees as the temperature of a mixture of ice water and ammonium chloride. So they tried to standardize this temperature, the Fahrenheit temperature, so you could replicate it in a lab. So with a specific mixture of water, ice, water, and ammonium chloride in specific quantities, you could drop the temperature down, right? Adding salt to ice lowers its melting point, or it lowers its freezing point, which is why you salt sidewalks in the winter. You can get down to 0 degrees Fahrenheit with this mixture. Now, problems with the Fahrenheit scale is that it's largely not used everywhere else in the world. Canada uses it a little bit, maybe Britain, but that's about it. So boiling point is 212 degrees Fahrenheit, freezing point is 32 degrees Fahrenheit. We're all familiar with those scales. But I like Fahrenheit, and I think the reason Fahrenheit has stuck around in the US is because it's a temperature scale that gives between 0 and 100 for everyday living, right? Most people don't experience temperatures outside of that range in their everyday lives, with the exception of people who live in northern Wisconsin in the winters, where it can get -10, -20 Fahrenheit pretty easily. most people live in the range between 0 degrees Fahrenheit for winter and 100 degrees Fahrenheit for the summer. So it's a fairly useful scale to represent the range of human experiences in temperature, right? And humans can just barely tell the difference between degrees Fahrenheit. You know, if it's 68 in a room or 69 in a room, as you walk from one room to another, you might notice that temperature difference, or you might not. It's just on the scale of noticing. Celsius degrees are larger, right? There's only 100 degrees between the freezing and boiling point of water, not 180. So one step on the Celsius scale is almost double a step on the Fahrenheit scale. So room temperature or changing a room 1 Celsius degree would definitely be noticeable. And a lot of people, when they do temperatures in Celsius, sometimes give that last decimal place. So Fahrenheit we deal with on an everyday basis. Celsius is very common in chemistry classes. In physics, we're going to be mainly using Celsius and Kelvin. Kelvin especially. Kelvin, ideally everyone would use because it is the absolute temperature scale. But sadly, physicists don't control the world, so we are stuck using these three. So we have to talk about how to convert between Kelvin, Celsius, and Fahrenheit. Common conversions that you'll need to use. Your book goes through them in more detail, giving you each equation, but all of you should have the algebra to be able to work backwards from one equation to the other. So here we have temperature in degrees Celsius is equal to whatever the temperature is in Kelvin minus the number 273.15. Alternatively, temperature in Kelvin will be temperature in Celsius plus that number. Now, when you have temperatures in Kelvin, do not say degrees Kelvin. The reason we say degrees Celsius and degrees Fahrenheit is because it's a relative scale. 0 does not represent actually 0, right? 0 degrees Celsius is the freezing point of water, but temperatures can be lower than that. 32 degrees Fahrenheit is the freezing point of water in the Fahrenheit scale. 0 degrees Fahrenheit is the temperature of some ice, water, and salt mix, but temperatures can get below that. Kelvin is an absolute temperature scale. 0 Kelvin is the lowest temperature you can get. So you should not say degrees Kelvin, although I probably will make that mistake, and I'm sure you will during the course of this semester. But just to be pedantic, I guess, the temperatures in Kelvin, you say this many Kelvin or kelvins for temperature. Temperatures in Fahrenheit, you say degrees Fahrenheit. Temperatures in Celsius, you say degrees Celsius. So temperature in degrees Fahrenheit, if you have degrees Celsius, take your degrees Celsius, multiply it by 9/5 and add 32. Algebraically, you can switch this around as I've done on the equation below. Temperatures in degrees Celsius is equal to the temperature in degrees Fahrenheit. First, subtract 32 and then multiply by 5/9. Now this 9/5 and this 5/9 comes from the size of the steps on those two scales. Remember that the temperature between freezing and boiling point of water is 100 steps on the Celsius scale. It's 180 steps on the Fahrenheit scale. 100 over 180 reduces down to 5/9. So this is basically 180 over 100, or 100 over 180. But we reduce the fraction down, of course. So these are simple conversions. With these three conversions, or even with these first two, you can go from Fahrenheit to Celsius to Kelvin, so Fahrenheit to Celsius to Kelvin, back and forth. Now, I talked about the triple point of water and how the Kelvin temperature scale is defined as 0 degrees at absolute 0 and 273.15, or 16, sorry, at the triple point of water. And the reason of that weird 273.16 Kelvin at the triple point of water is due to the fact that the Celsius scale was already well established in chemistry and in physics. But to use an absolute temperature scale, we wanted to pick, physicists and chemists wanted to pick an absolute temperature scale that had the same step size as the Celsius scale did. So 1 Kelvin is the same size as 1 Celsius degree. So there are 100 kelvins between the boiling and freezing point of water at sea level. There are 100 Celsius degrees between the boiling and freezing point of water at sea level. So that's why the Kelvin has that weird definition. so the step sizes are the same. Now, the triple point of water is used because it is a constant regardless of what pressure you're in, where you are on the earth, what laboratory you're in. When we create these standards, we want SI standards, we want standards that can be replicated anywhere, ideally anywhere in the universe. The length of a meter is actually dependent upon the speed of light. The length of a second is dependent upon a vibrational frequency, a very specific, I believe it's cesium, cesium isotope, which can be found anywhere in the universe. The triple point of water is just, if you take a container where you can change the pressure and the temperature in the container, sealed container, at 0.01 degrees Celsius and at 0.006 atmospheres, so that's 0.6% of the atmosphere at sea level, something interesting happens to water. Water can exist at that point in all three forms. Now, if you change the temperature of water, you change its state. You can change its state, right? All of you know this, right? You throw water in the freezer, it becomes solid. You throw water on the stove, turn it on, it becomes a gas, right? You boil the water, turn the water into water vapor. Liquid water into water vapor. But that actually works with pressure, and I talked a little bit about that with the boiling changes due to living in Denver, for instance. So changing the pressure can also change the temperatures where these states change. But at this specific temperature, 0.01 Celsius, at this specific pressure, 0.006 atmospheres, something interesting happens with water. Water exists in all three states. So you have in your glass tube, at this pressure, at this temperature, solid water ice, liquid water, and water vapor. And they all exist happily. The water ice is not melting. Actually, I should say it's melting a little bit, but then the liquid is freezing at the same rate. The liquid might be evaporating into water vapor, but the water vapor is condensing at the same rate. All three states coexist happily. And that only occurs at this temperature, at this pressure. So if we were to communicate with alien civilization in another planet, and they want to know, well, how do you guys measure temperature? We can give them this. Water is ubiquitous in the universe. It's a very simple molecule. And they can actually figure out our temperature scale using this standard, as can, of course, any lab in the world. So that's the advantage of using, the triple point of water as this standard. Your book then talks about the Zeroth Law of thermodynamics. And since we've defined temperature, we can talk about this Zeroth Law. Now that is an odd name, the Zeroth Law. Why do they call it the Zeroth Law? Well, actually, it was forgotten about after the first and second laws of thermodynamics were discovered and codified. So on the books, physicists already had the first and second laws of thermodynamics, but people pointed out, well, for those two to be true, the first and the second law, this has to be true first. And we'll talk about what this is in a moment. So physicists went back and went, oh, great, what do we call it? Do we rename the laws? Oh, well, what comes before one? Oh, zero does. We'll just call it the Zeroth Law. So odd name with an odd history. The technical definition, if bodies A and B, so you have two objects A and B, are in thermal equilibrium with a third body, C, then they are in thermal equilibrium with each other. What does that mean? Well, you can think of it shown here in red, right? Objects in thermal equilibrium are the same temperature. So if I have two mugs of water sitting out on my desk, and I stick a thermometer in mug A, and it reads, say, 70 degrees Fahrenheit. And I stick the same thermometer, I put it in mug B, and it says 70 degrees Fahrenheit. I let it rest for a while, it still says 70 degrees Fahrenheit. Those two mugs are in thermodynamic equilibrium with body C, the thermometer. So first mug is mug A, the second mug is mug B, the thermometer is body C. Body C is in thermodynamic equilibrium with both A and B. Both of them read 70 degrees Fahrenheit. Therefore, the water in mugs A and B are at the same temperature. They're in thermal equilibrium with one another, which means if I pour mug A into mug B or mug B into mug A, the temperature will still be 70 degrees Fahrenheit. Right? Barring a chemical reaction that releases heat or exothermic or endothermic that takes in heat during the reaction. Think of those cold packs where you start a chemical reaction before you put it on your injury. If it's just plain water, there's no chemical reaction, temperatures won't change, right? If you have a bathtub at 65 degrees Fahrenheit and you have a mug of water at 65 degrees Fahrenheit and you pour the mug of water in the bathtub water doesn't change temperature. Now that seems like, well, duh, but it's actually an important feature because it's not just the same like water with water, it's any object. If I have a bathtub at 70 degrees Fahrenheit and I have a giant metal ball at 70 degrees Fahrenheit and I drop that metal ball in the water temperature doesn't change. Now, if that ball isn't 70 degrees, if it's colder or hotter, then you have heat transfer between the ball of metal and the water. And we'll talk about heat transfer in a bit. So this is the Zeroth Law of thermodynamics dealing with temperatures of objects. So temperature is an important measure of the energy, the thermal energy within an object. Sorry, addendum. Temperature is not a direct measure of the thermal energy within an object, but it's an important part of that measurement. For example, a mug of water at 200 degrees Fahrenheit has quite a bit of thermal energy compared to tepid water, room temperature water. But a bathtub of water at 200 degrees Fahrenheit has far more thermal energy. So it's not just a matter of temperature, but quantity as well when dealing with the amount of thermal energy. We'll talk about that in a bit.